Let's kick things off with a pretty fundamental question. For thousands of years, geometry was completely static. Think of ancient mathematicians sketching fixed, unmoving shapes in the sand. But our world today, it's completely dynamic. So how do we actually shift shapes around? How do we transition from those old school static drawings to what we call transformational geometry? Basically, how do we mathematically move objects across a plane without changing their fundamental size or shape? Welcome, grade 9 students at St. Paul American School, Clark, to today's Explainer. We are going to totally master the geometry of movement. I'm honestly so thrilled to guide you through this because once you get how math actually governs movement, I promise you're going to see the physical world completely differently. Today, we're strictly focusing on two really powerful types of movement: translations and reflections. All right, here's our quick roadmap for today. We've got our objective, a breakdown of the math, a worked example, a misconception check to clear up any confusion, a quick formative check, and finally, a wrap-up with our concept recap. Let's get right into it. Section 1. Objective: the geometry of movement. Okay, to really understand how figures map from one place to another, try using this mental model. Picture a static grid on a piece of paper, and right on top of it, a clear sheet of transparency paper. Whenever we move a shape, we aren't painstakingly redrawing it from scratch. Instead, imagine we're just sliding or flipping that top transparency paper over the static grid underneath it. This brings us right to a massive concept: rigid motion. A rigid motion is a transformation of the plane that takes lines to lines and perfectly preserves the exact lengths of line segments and the exact measures of angles. When you move that imaginary transparency paper, you are literally performing a rigid motion. You're moving an object without stretching it, shrinking it, or wrinkling the paper. It maintains its absolute original size and shape. We call the original starting figure the preimage, and the new, moved figure the image. Section 2. Explanation, translations, and reflections. Let's check out our first core transformation. A vector explicitly gives us the exact distance and direction to slide our imaginary transparency paper. A translation is entirely determined by this vector. It's essentially a set of instructions. It tells point C exactly how far to slide and in exactly what direction to go to become its new mapped image, C'. There's zero guesswork here. Every single point on your shape moves identically along its own parallel vector. Now, because a translation is just a smooth, flat slide of that transparency paper, it follows some really strict rules. When we do this slide, horizontal lines stay horizontal, and vertical lines stay vertical. The segment lengths and the degrees of all the angles, perfectly preserved. If you look at the preimage and the newly translated image side by side, they are visually identical. On top of that, a translation always maps a line to a parallel line. The slope never, ever changes, not even a little bit. All right. Alternatively, we have reflections, and a reflection requires us to do something slightly different with our mental model. Instead of sliding, we have to actually lift that transparency paper in 3 dimensions and fold it over a specific line, which we call the line of reflection. This acts exactly like a mirror. Every single point on the pre-image is reflected to the opposite side of the line, sitting at an equal distance. And here's an incredibly important detail. Any point that's already sitting directly on the line of reflection stays completely fixed. It doesn't move at all. It's anchored right there. This brings up a brilliant contrast between our two rigid motions. Yes, they both perfectly preserve size and shape, but we need to talk about orientation, the sequence or order of the points. Here's the deal. Translations preserve orientation. If you trace the points of your original shape and they follow a clockwise order, they will still be in that exact clockwise order after a translation. But reflections reverse orientation. Think about looking in a backroom mirror. Your left hand appears on the right side of your reflection. Reflections flip that sequence, changing the orientation entirely. Moving on to Section 3. Worked example, coordinate rules. So it's one thing to imagine sliding paper around in your head, but let's actually apply these visual concepts to a specific algebraic model. Let's see exactly how we calculate these moves using real numbers on a coordinate plane. Take a look at the coordinate rule for a translation. It's actually remarkably elegant. To translate any point, all we do is identify our vector, which gives us a horizontal value A and a vertical value B. We grab our original pre-image coordinates, x and y, and we just add them together. So the rule is simply x, y maps to x plus a, y plus b. By doing this simple addition for every vertex of a shape, we accurately plot the entirely new image without altering its dimensions at all. By sliding our shape along the specific vector PQ, we can prove mathematically that a translation maps a line strictly to a parallel line. Think about it. Because our algebraic rule adds the exact same horizontal and vertical values to every single point, the rise over run remains totally identical. Therefore, preserving the slope entirely is a guaranteed hard and fast property of translations.
Section 4. Misconception check. Spotting the errors. Before we push forward, we definitely need to clear up a few subtle errors that tend to trip students up. First up is a common misconception about infinite lines. Sometimes it's easy to think that if you translate a line and then extend both the pre-image and the image out infinitely forever, they might eventually cross paths somewhere way down the line. But remember, because translations strictly preserve slopes, the original line and the translated line are perfectly parallel. Unless the translation vector slides the line exactly along itself, those two lines will absolutely, positively never intersect, no matter how far out you draw them.
And here's another one. Assuming a reflected image is identical to a translated image, just sort of dropped in a different location. Visually, at a quick glance, they might look like the exact same shape, but mathematically, this is completely incorrect. As we established earlier with our mirror analogy, a reflection inherently reverses the orientation of the shape. It fundamentally changes the sequence of the points, whereas a translation keeps that exact same orientation. They are totally distinct types of rigid motion. You literally can't swap one for the other.
Section 5. Formative check. Test your knowledge. Okay, let's put your geometric intuition to the test with a quick mental scenario based on the rules we just went over. Imagine a point P just floating in space. Now reflect it completely across a mirror line, which we'll call line L. That gives you your new image, P'. Now, I want you to imagine drawing a straight line segment connecting the original point P directly to the new image P'. Think back to folding that transparency paper across the mirror line. What exactly is the geometric relationship between the mirror line L and that new segment you just drew?
Well, if you pictured a cross, you hit the nail right on the head. The answer is that line L is the perpendicular bisector of segment P'. Because a reflection perfectly preserves length and angles, the mirror line cuts the segment exactly in half. That's the bisector part of it. And it does so at a perfect 90-degree angle. That's the perpendicular part. The distance from your original point P to the mirror is exactly equal to the distance from the mirror to your new image, P'.
Section 6. Concept recap. You guys did excellent work today. We've covered a lot of ground, moving from the intuition of sliding paper all the way to the algebraic reality of coordinate rules. So here are your absolute core takeaways. Translations slide an object along a specific vector, moving every single point the exact same distance and direction. Reflections flip an object across a specific line of reflection, acting just like a mirror. Crucially, both of these are rigid motions. They map lines to lines without ever altering their measurements, perfectly preserving the size, the length, and the angles. But always remember, while translations keep the figure facing the exact same way, reflections entirely reverse its orientation. So the next time you look into a mirror to check your reflection, or even just slide a digital image across the screen of your phone, I want you to ask yourself, how is this rigid motion mathematically calculating my image right now? What hidden vectors and lines of reflection are operating behind the scenes to make that happen? Keep observing the geometry of movement in your daily life, and I really hope this explainer leaves you seeing the math behind every single slide and flip. See you next time.